Various definitions of strain, and we selected the Bajorquez strain tensor as the one that we will use for the predominant part of the course. But I should also mention that the green Lagrange strain is also sometimes very convenient, especially when you are using a nonlinear analysis for the cross section, the kind of effects that we talked about, like Bezier effect and trapeze effect in earlier classes. Many of those would be much more tractable when you use the green Lagrange strain. In other words, the derivation would be more convenient. But irrespective of which definition you use, eventually the final result should be the same. It's only a matter of convenience and using the appropriate conjugates when you go to the stresses. In today's class, what we will do is we'll take up local rotations. We introduced these concepts over the course, but in the previous class we mentioned a few more aspects about local rotations. We'll take that a little further and discuss about the orders of magnitude of local rotations in various classes of beams that we already classified beams generally into. If you recollect the class R, S and T. And for those classes, what are the typical orders of local rotation is what we will speculate upon. At this point, we can only speculate upon because we have not actually derived the expressions for the 3D strains, at which point of time we will be able to come back and verify what we speculate upon today. Once we are done with that, we speculate upon the orders of the magnitude of the various local rotations in various classes of beams. We'll take up a simple example to show how we can formulate the kinematics of beams, and in this simple example we'll make certain ad hoc assumptions. We've been actually warning against ad hoc assumptions, but for pedagogical purposes, for the illustration in the class, we will make certain ad hoc assumptions in today's class, and later, probably most probably in the next class, we will try to revoke those ad hoc assumptions and do it for the more general case. The only reason we are doing this here is that the explanation would be much clearer for this simpler example. And again, ad hoc assumption does not necessarily mean an invalid assumption. Ad hoc, what it means is that it is valid for some special cases or for some narrower class of problems. So for those it is still valid, just that it is not valid for a much more general class of problems, which is what we intend our theory eventually to be. So what we introduced in the last class was the Bajorquez strain. What we will do now is try to simplify that further. We already did one level of simplification by going from the tensorial representation of the strain to the matrix representation when we expanded out the Bajorquez strain in the undeformed basis vectors. So once we did that, we had a matrix equation. So what we will do now is to look at what happens to that equation, supposing the local rotations orders of magnitude were known. And of course, we are dealing with engineering materials where the strain is small, so that assumption is already in place and it's a valid assumption. But as of now, we don't know whether local rotation is small or not, but later we will show that the strain directly depends on the local rotation, and if the local rotations were large, then our original assumption that the strain is small would be violated, and that's the reason why the local rotations are small too. But how small they are varies between the various classes of beams depending on the cross section. So this is the expression we had at the end of the previous class, a matrix expression for the 3D strain, the Bajorquez strain, and of course it is a symmetric matrix. So there are 6 independent components there associated with the 3 normal strains and the 3 shear strains. And then you see that it is entirely expressed in terms of 2 deformation variables. One is basically the local rotation expressed here in a skew symmetric matrix form, and then you have the deformation gradient tensor, which is in general an asymmetric matrix. So in terms of these 2 deformation quantities, this is defined. But if you recollect the original definition for the Bajorquez strain tensor using the Seith-Hill family criteria, this whole thing was just U. So it's just that we had reduced that U, the right stretch tensor, and then again converted in the matrix notation after the expansion and expressing it in terms of the various rotations, global as well as local. We eliminated, and this particular relationship is a general result which is valid irrespective of whether your local rotation is small, medium, moderate, large, whatever, and even in the case where the strain is not necessarily small. So far we have not even made that assumption that the strains are small. So this particular expression is valid even for the case of large strains, for example for hyperelastic materials. Just that this kind of a definition for strain becomes inconvenient when dealing with hyperelastic materials, and in such situations we go for other types of definitions for the strain. But coming back to the regular engineering materials where small strains are to be used, we will try to basically reduce this further. Though in terms of the way this equation is written here, it looks very compact and simple. It is in the determination of this that you will face a lot of complications, especially because of the exponential term here. And it's precisely for that reason that we need to take advantage of what is small in this particular problem, and that's what the variation asymptotic method eventually anyway would take advantage of for the dimensional reduction purpose. So what we take advantage of is not only the small strain but also the order of magnitude of the local rotations. So what we will do is we will introduce two new symbols here, epsilon hat and phi, to denote the orders of magnitude of two quantities. One is the strain and the other is basically the local rotations. So when we say it is the order of magnitude of a strain, what it means is that it is the largest possible value for any one of the 6 strain components anywhere within the entire domain of the beam, along its length, along its cross sections, and at any point of time in the interval being considered for a dynamic problem. So that's what epsilon hat refers to. And then if you look at phi, then that is basically similarly it's the largest value of the local rotation. Remember that there are 3 components to the local rotation in general, and it is the largest value of all of those 3, and once again within the entire domain of the beam and in the entire domain of the time interval being considered. So mathematically speaking, what that means is that it is the maximum. Of course, I have left out the t here, but that is implied. So in a dynamic problem, that you have to include time as an independent variable here as well. But all the derivations still hold, irrespective of whether this is a static or dynamic problem. So the maximum magnitude, because you're not looking at the signs here, so it's the maximum magnitude of gamma ij, which is referred to as epsilon hat, and because of the fact that engineering materials undergo a maximum of about 1 or 2% strain, it is quite okay or acceptable to use this assumption that epsilon hat is small compared to unity. Similarly, this local rotation, which is the maximum value of any of the components phi tilde ij, which of course are only 3 independent quantities, namely the phi1, phi2, phi3 components of the local rotation vector, and which are just put in an skew symmetric form. So in any case, phi11, phi22 and phi33 are zeros. It's only the off diagonal terms, and again on one side of the diagonal that we are interested in, and the maximum of that anywhere in the domain is basically small compared to 1. Of course, the reason for this, as I said, will follow from this, but right now we don't have the mathematical proof for that. Right? Retain only the terms of the lowest order in epsilon hat and phi. This is something that I mentioned before, but no harm in repeating the fact that lowest order means leading terms. So people new to asymptotic techniques, not only variation asymptotic techniques, but any asymptotic techniques typically make this mistake. But please remember that lowest order means, when we are talking about orders, we are talking about the powers in the small parameters. So the lowest order basically means the largest terms in size, or in other words, the leading order terms. So to start with, because we always go for the leading order terms first, so that we can get the 0th order approximation. Of course, everything has to be eventually done in terms of the total potential, what are the leading order terms. but at this point of time we are only focusing on the kinematics, so we will discuss only those aspects right now. So retain only the terms of the lowest order in both these small parameters that we have, but we do need to of course understand the relative orders of magnitude of these small parameters, because I think we discussed this once in the context of the two types of small parameters that we have in the beam as a whole. Some are the geometric small parameters and the other is the strain itself, and each of these are different types of small parameters. One is a physical small parameter, namely the strain, the others are geometric, and a relationship between these is essential in applying the variation asymptotic method, because you need to say which are the leading terms, and some of these terms depend on each of these small parameters, and therefore without knowing the relative orders of magnitude it becomes impossible to say which is the leading order term. So similarly in this case, when we are looking purely at kinematics, we are looking at the need for understanding the relative orders of magnitude of these. Once again, that cannot be said until we derive, but what we will do is just to speculate upon and show how it is different for the different classes of beams, and later on take it up when we have the expressions for the strain itself. So now let's say we have a Taylor's expansion of the exponential term here in this definition. So if you have exponential of minus p tilde, just like the exponential of any scalar quantity, it involves, for example, exponential of x would be 1 plus x squared by 2 plus x cubed by 6, etc. So x power n divided by n factorial, where summation from n is equal to 1 to infinity. So that's basically what you have over here, rather n is equal to 0 to infinity. So that's basically what you have here, and because in any case we are going to look at small local rotations, we have not we have truncated it at a particular point in the power series, but probably some of these higher powers are also not necessary. We'll look at it when we do the derivations. So to expand the deformation gradient tensor expressed as a matrix in mixed basis, which is what we have as chi over here, as opposed to a chi with a double underline, which is what we dealt with in the previous class, where that was basically the tensorial notation, and once we introduced the mixed basis of the small b and the big B system to expand that out, we got this 3 by 3 matrix, which is an asymmetric matrix, neither symmetric nor antisymmetric in general. So already we said that gamma depends on these two quantities. Now we have a way of representing this exponential using this Taylor series. Now let's see what we can do with the other deformation quantity here, chi. So to expand chi, or the deformation gradient tensor, what we will do is we'll now break it up into 3 parts. Typically, you know how you break up a matrix into 2 parts. One is the symmetric part and the antisymmetric part. The matrix plus its transpose divided by 2 would be the symmetric part, and the matrix minus its transpose whole divided by 2 would be its antisymmetric part. But in this case, we'll also break it up into an additional part, because remember that the deformation gradient tensor, if the beam remains undeformed, is nothing but an identity matrix. So in other words, remember that what the deformation gradient tensor does is to take the covariant basis vectors of the undeformed configuration and convert it to that in the deformed configuration. So if there was no deformation at all, no loading and therefore no deformation, then what should happen? Basically, the big G subscript I should be the same as the small g subscript I, which means that the deformation gradient tensor should not be nothing but the identity dyadic, or in other words, in a matrix notation, it would be just the identity matrix. So instead of breaking it up into just a symmetric and antisymmetric part, we'll break it up into 3. One is the diagonal part, which is the identity matrix itself, and then the other 2 over here. So that's what we would do. So to do that, we will define this quantity E as the symmetric part minus the identity dyadic, or rather matrix, and then we'll talk about an antisymmetric part, for which we will use the usual symbol of tilde that we utilize. But of course, it doesn't have the same functional notation, because that is typically used over a vector notation, but this is used over a dyadic notation, and that which is converted already to a matrix, is just to mention the fact or stress on the fact that this is an antisymmetric matrix that we are basically using chi tilde. So that of course is just chi minus chi transpose divided by 2. So if this is the case, then it's quite obvious that your chi can now be broken up into 3 parts. One is delta itself, the other is E, so that when they get added, you just get the symmetric part of chi, and then the third part would be the chi tilde, which is the antisymmetric part. So this is what I mean. So you've now broken up chi into 3 parts, the identity matrix, E, and chi tilde. And this E has a special meaning. If you recollect when we introduced the various ways in which the strain tensor could be defined, this was in fact, E was one of the things that we had defined, which is whose work rate conjugate stress is basically the Kirchhoff stress. So that's something which is very commonly used, and it will play a very important role. And especially when you're having a problem, let's say for example with R-class beams, where it happens to be a linear cross-sectional problem, in such a situation the entire strain can be represented as E itself, as we shall shortly see. So that's why that plays a very important role. Of course, as I said, when there is no deformation, this is what happens. So that takes care of that. And this is when you have a linear problem, this is what happens when local rotations are not important. Whereas chi tilde typically is predominantly something which is contributed by the local rotation. So we'll soon see, after we make the derivation, that chi tilde is dominated by the local rotations to such an extent that if the local rotation were not 0, this would pretty much vanish. So in other words, the entire deformation gradient tensor would be given by just these, or in other words, the strain would be contained in this. And that again gels well with what we mentioned, that for a linear cross-sectional analysis, E alone is sufficient, which is also what we will see shortly. But basically, it's important to remember that your E contains this basic strain part, and this is what contains the local rotation part. Though, of course, eventually both would contribute to the total strain if you're going for a higher order analysis or a nonlinear analysis. So now let's focus on this antisymmetric part of the deformation gradient tensor, chi tilde. I already gave you a hint that it is going to be something which is going to be dependent on the local rotations. Let's see why this really happens by doing some matrix manipulations over here. So I'm repeating the equation that we had at the end of the previous slide, where we broke up chi into 3 parts. Now we'll substitute that into the equation that we derived at the end of last class, which is for the Bjorkman-Cauchy strain tensor in terms of the local rotation and the deformation gradient tensor. So we'll substitute this blue quantity in lieu of this blue quantity over here, and we will solve for E. So that is quite straightforward. All that I do is I put this delta plus E plus chi tilde over here. I take this delta to the left hand side, and then I have in this delta plus E plus chi tilde, I just have to solve for E. So I can multiply both the sides by exponential plus phi tilde, so that in this right hand side it will get cancelled, and when I do that, I can bring the other two quantities which are over here to the right hand side, that is delta and chi tilde, with a minus sign. And so it is straightforward to see that your E is going to be now be given by exponential of phi tilde multiplied with the identity plus the Bjorkman-Cauchy strain tensor, strain matrix, minus the identity matrix and the antisymmetric part of the deformation gradient tensor. We'll do a few more manipulations here. Now we know that E is a symmetric matrix by definition, because remember that we defined it as chi plus chi transpose divided by 2 minus delta. Chi plus chi transpose by 2 is symmetric, and delta is symmetric as well, and therefore E is symmetric. Now we take advantage of that, so we can equate E to E transpose, because E is symmetric. To get E transpose, of course, we have to take the transpose of each of these terms, the 3 terms that it has. Delta's transpose is delta itself. Chi tilde's transpose would be minus chi tilde, so this minus would become plus. And this is the transpose of a product of 2 matrices. So basically the transpose would become the transpose of this multiplied by the transpose of this. and the transpose of this, because it is a rotation just like any other finite rotation tensor, it would just be the transpose is also the inverse, or in other words, it would just become exponential of minus phi tilde. So once we do that and equate E and E transpose, this is what would happen. We could solve for chi tilde. So that matrix equation, we can eliminate chi tilde and we can just see what chi tilde is in terms of the Jaumann-Bioy-Cauchy strain tensor and the local rotation. So it's a straightforward manipulation once again. So all that we have now is the subtraction of two terms which look very similar, but in a sense there's some kind of an inverse of one another because of the plus phi tilde there and the minus phi tilde here. So that is what chi tilde is. We can do a few more manipulations eventually to reduce chi tilde to a much more straightforward expression in terms of phi tilde, which is what we will do now. For that, we will go ahead and invoke the fact that the local rotations are small. So to take advantage of that, we will go to the Taylor series. Right now we will not truncate it, but basically add on the terms saying what is the order of magnitude of them in terms of the quantity phi that we introduced as the maximum value of the amplitudes of the local rotation anywhere in the domain of the structure within the time interval of interest. So this is basically what it is for exponential minus phi tilde. We need that, as well as we need exponential positive phi tilde, for which of course all these signs just become plus. So it is similar to that equation. So once we do that and we simplify, it turns out that your antisymmetric part of the deformation gradient matrix is the leading term is nothing but phi tilde itself. So in other words, you see that the dominant term there is phi tilde, and in fact next term is phi tilde cube divided by 6. So if phi tilde were 0, in other words there was no local rotation in the problem, which would be the case, for example, if you had no warping. Okay, so in an Euler-Bernoulli beam theory, for example, there is no warping. If there is no warping, there cannot be any local rotation. There can be a situation where you have warping but no local rotation, because warping is more than local rotation. It could involve other kinds of deformations as well. But basically, if the local rotations were 0, then basically, if the warping were 0, then local rotations would be 0, and in turn your chi tilde would be 0 as well. So this is what you have, and you can also see the remaining terms, what their orders of magnitude. Some are purely dependent on phi, like the first two terms, and those would be of the order of phi power 4 in terms of the same small quantity that we already introduced. And there are terms like these which involve both the local rotation and the strain. So that those terms would have a combination of phi and epsilon hat, where epsilon hat is the maximum value of the strain that we also introduced at the beginning of today's class. So this is what we have for chi tilde, which is the antisymmetric part of the deformation gradient tensor. Now we'll go ahead and look at how we can simplify this for the case of small strain and small local rotation as well, and also a case of moderate local rotation, and we'll specifically mention what we mean by each of those. So this is just repeating what we had as the result at the end of the previous slide. Now we substitute this result for the antisymmetric part of the deformation gradient tensor, and one more thing, which is basically the Taylor series, into the expression that we had in the slide previous to the last one, which is basically the expression for the symmetric part of the deformation gradient tensor without the identity matrix. So that is what E was. So now we remember that we had derived this equation in that slide. E is equal to exponential phi tilde into identity matrix plus Jaumann-Bioy-Cauchy strain matrix minus delta minus chi tilde. So now we will substitute for this chi tilde using this, and for the exponential phi tilde using this. Once we do that, we can, of course, a little bit of manipulation is required, and once you simplify that, now you see that as far as the symmetric part of the deformation gradient tensor without the identity matrix is concerned, that is E, the leading part is now nothing but your Jaumann-Bioy-Cauchy strain tensor itself. So that is what it is. And then of course there are contributions from the local rotation as well as higher order terms, and you could see over here. When you're looking at situations where, for example, the trapeze effect, brazier effect are important, which are basically in thin-walled structures, thin-walled beams, in such a situation local rotations will dominate, and then these additional terms could become important as well. But in an R-class beam, which is not thin-walled basically, in such a situation you would see that the dominant term is just this gamma. In other words, you invert this relationship and say that your Bjorkman-Cauchy strain tensor or strain matrix is nothing but the symmetric part of the deformation gradient tensor minus identity alone. There is no other contribution. So that is an interesting result that we get out of this. Now we will solve this particular equation for gamma, which is again involves a few matrix manipulations and taking advantage of the fact that phi tilde is an antisymmetric matrix. So that results in a few simplifications. And once we do that, to solve this, you can see that gamma is going to be now be given by E minus phi tilde squared plus E phi tilde minus phi tilde E divided by 2, and then you have higher order terms which are put to the power of 4 in the local rotation, and also mixed terms which involve epsilon hat as well. So now the question is, when can higher order terms be neglected? So for example, these plus order of phi power 4 phi squared epsilon hat that we are writing over here, not only for gamma but also for chi tilde over here, when can they be neglected? So that is something which once again leads us to the original classification we had for the various classes of beams in terms of the cross-sectional shapes and whether certain small parameters exist in the geometry of the cross-section itself. So material failure strain limits of course imply that epsilon hat is very small compared to 1, so that is a straightforward thing to decide with respect to terms which involve epsilon hat. The only question now that remains is for the terms with respect to phi, because we don't yet have an expression for the 3D strain in terms of the local rotation. So that is the reason why we are stuck over here. So the 3D strain local rotation relation is to be determined later. But for now, let this phi be related, as I said, in order to apply later on the variation asymptotic method, which we will do only after we are able to have an expression for the strain energy, because that's the stage at which we can apply that method. But for that, as I said, when we have multiple small parameters, we need to have a relationship between them. So let's say phi is given, again these are orders of magnitude only, we are not talking of actual numerical values. So it's only the orders of magnitude that we are considering. Let's say phi is of the order of epsilon hat power r, where r can be anything. So so let's take two separate ranges of r, because that will help us classify, and we can see that this is what happens with respect to the various classes of beams. Because r is the entire domain of real numbers, so basically what we are doing is we are saying that r is greater than or equal to 1 and r is less than 1. So these are the two cases that we are basically looking at. Again, if we'll have situations that r cannot be negative, because if r is negative, then because epsilon hat is a small parameter, then phi will no longer be a small parameter, because it will become 1 divided by a small parameter, so it will become a large parameter, which is not the case indeed. But so in this particular range, when we say r is less than 1, there are negative values are precluded. Even values which are say less than half, for example, will be precluded, because if you see some of the expressions for the strain, you would see that some of the terms, like in gamma, this term will start dominating over this particular term. Again, all of these are speculation, as I said at the very beginning of the class. The proof of the pudding would only be when you actually have the expressions for gamma. But these are things that we can observe, and they are interesting as well. So now we said that we are going to take the relative orders of magnitude by introducing a parameter r, such that phi is of the order of epsilon hat power r. Now we look at a few cases of this r. The first case is when r is large, basically greater than 1 or equal to 1, which means that what we refer to hereafter as small local rotations. because remember the larger r is, then because epsilon hat is smaller compared to 1, then phi will become even more smaller. So in terms of the size, the magnitude. So that's why large r means small local rotation. So now the theory based on this range for r, we will later on see, is suitable for primarily class R beams, because there you will see that the maximum curvatures that are there will be fairly small, because the strain will be dictated by the curvature times the cross-sectional dimension, and because there are no small dimensions in the cross-section, basically this is what happens. On the other hand, in the case of the other two classes, namely class S and class T, there are certain small dimensions, and therefore the strain is now still the cross-sectional dimension times the curvatures, and therefore the curvatures can be larger in such situations, and the curvatures are the ones which predominantly dominate these local rotations. That again will become clearer only when we have the actual expressions. Not only is this valid for class R beams, but also for class S beams under some special considerations. For example, if you have some special kind of loadings, you know that the trapeze effect becomes important because it is an extension twist kind of a coupling. Suppose there are no extensional loads at all, or extension strain is not a load, two different cases. In such situations, you would see that the local rotations even in an S class beam would not be large, and in such a situation, even there a small local rotation assumption would not give highly erroneous results. They would be acceptable within engineering tolerances. So this is the second category for which it could be applicable for class S beams under some special loading cases. For example, if it is not axially loaded. Then of course, because local rotation is primarily driven by warping, all that this means, remember that local rotation, as I've always been saying, is basically the rotations of small elements within the cross section about the three directions. I talked about elements of linear elements. It could be aerial elements as well. So you can talk about aerial elements. That will give a clearer picture why there are three components. Okay, so, and as I said, they are predominantly dictated by a W1, 2 or a W1, 3, similarly a W2, 1, W2, 3, etc. Basically derivatives of warping with respect to the other cross-sectional directions other than what direction that warping component itself is in. So, so from that it becomes clearer that if the local rotations were small, then the warping would be small as well, or vice versa, because of the fact that it's the warping which contributes towards the local rotation. So then the warping gradients in the cross-sectional plane of the same order, because it's an R class beam, for example. Let's forget the second example that I gave for now, because it comes under some special loading cases for which further restrictions will be involved. Let's focus just on the class R beams. We know that the cross-sectional plane, both the thickness as well as the width are of the same order of magnitude for a class R beam, and therefore the warping gradients in any direction that you take within the cross-section would be of the same order of magnitude. Numerically, though they might be different, they are of the same order of magnitude. So again, we are talking about the largest values they can take before failure happens or the design limit loads are reached. So then the local rotation effect is negligible in such situations. That is why we call that as a small local rotation case. And the strain for this case reduces to, if you remember the expression that we had for gamma in the previous slide, the leading term there was E, and then you had a phi tilde squared term. So if that is such that your R is greater than or equal to 1, and you see the relationship between phi and epsilon hat, because the leading terms gamma would be of the order of epsilon hat, and therefore E would be of the order of epsilon hat, and so that would be a higher order term. So when you are looking at, let's say, only for the so-called zeroth order approximation or the leading order term approximation, then just taking gamma to be E alone, which is the symmetric part of the deformation gradient matrix, minus delta or the identity matrix, is basically sufficient.
So, can you repeat the second point, warping variations cross-section?
This one?
Yeah.
Yeah. See, basically you have a class R beam like this. So what we are saying is that it could be a square cross-section or rectangular cross-section with the thickness and width of the same order of magnitude, though not numerically different, though numerically they could be different, okay? It could even be a circular solid cross-section for that matter. In all such situations, you see that whatever the warping values are, they are functions apart from x1 and time, or they are functions of x2 and x3, okay? So now local rotations is basically, if you take a small square element over there, it is rotating about this direction, it is rotating in this direction, it is rotating in this direction as well. So it's basically rotating in about all the three directions, which is what, and of course if you average that out throughout the cross section, it has to go to 0 because the global rotations have already been taken into account. So that's basically what we are saying. Now, for example, let's say I introduce coordinates x1 along this direction, x2 along this, and x3 along this direction, vertical direction. So now you see that suppose there is a w1, so that w1, let us say, varies with x3, okay? So which means that there will be a rotation like this, w1 comma 3, okay? And that is different at different locations along the cross section. So now the w1 comma 3, the derivative with respect to 3 would be of the order of magnitude of the thickness. Similarly, a w1 comma 2 would be a derivative with respect to the width coordinate. Now the width and the thickness are of the same order of magnitude. So a derivative of w1 with either with respect to x2 or with respect to x3 would not make a difference. So that is basically what we are talking about here. Of course, w1 comma 1 is not a rotation. It is basically contributing to the axial strain, so that's not something we are bothered about. And there, of course, the derivative with respect to 1 is a much larger quantity in terms of orders of magnitude because the length is much larger than the cross-sectional dimension. So in class R beams, the warping gradients, in other words, W1, 2, W1, 3 that we discussed, and similarly W2, 1 and W2, 3, etc. So those 6 kind of gradients that we're talking about, which contribute to the local rotations, would all be of the same order of magnitude. So that is what is an important point over here. So that what that means is that in turn there is no one component of the local rotation which can become predominantly large, as it would, for example, in a D-class beam, those associated with torsion. So there can be certain large warpings, and the derivative of those warpings, for example, in this case with a strip case, when there is an axial load, there is a torsion, and then you would see that a derivative of W1 with respect to the x3 coordinate, for example, is much larger than the derivative of W1 with respect to the x2 coordinate. And in such situation, one of the local rotation components can be such that R is less than 1. So in other words, the local rotation magnitudes are larger, and therefore you cannot restrict your gamma to just E. You might have to consider the other terms in order to get a reasonably accurate result for any of your engineering properties. So next, this range for R that we talk about in this slide, R greater than or equal to 1, results in a linear cross-sectional analysis. Again, that is also clear from the fact that gamma is equal to E, and E is nothing but just the symmetric part of your deformation gradient tensor, and you can see that that is what will only contribute as far as a linear analysis is concerned. In other words, the cross-sectional deformations are not very critical there. So everything can be obtained predominantly from the global rotations and the global translations. So that alone would be pretty much sufficient. But of course, you can have, for example, warping components which are contributing without local rotation. So that is also possible. So something like a W2, 2 or a W3, 3 kind of terms could still be contributing some kind of energy to the strain energy, total strain energy, or to the total potential, which is not negligible.
Why is class B beams with that axial, non-axial loading not considered?
Oh, because as soon as the axial load comes, the torsion is encountered, and that because of the fact that it is torsionally soft, that in turn induces local rotations. On the other hand, for example, if you don't have an axial load, you have only torque, for example, then you still have warpings taking place, but because there is no axial load, there is not much of this W1 derivative with respect to X3. Okay, the W1 gets further accentuated when in the presence of the axial load, and that's what causes the large nonlinear term in the trapeze effect, even for isotropic beams. Okay, let's look at the second category. That's basically, we looked at a range of R in the previous slide. We look at the other range of R, and as I said, if it is lesser than half, the local rotation starts to dominate over and above the global rotations, and that is global rotations and the global translations, and that is usually not the case what is observed. So it is not necessary for us to look for values of R lesser than half. So let's look at this range from half to 1 and see what basically happens, and this is something that we will call as moderate local rotation as opposed to small local rotation in the previous slide.
So R gets less than half in case of like hydroelastic material and things like that, right?
That's again something which is debatable, because you see in that case the strain is large.
Yeah.
See, the strain is large, so the question of an epsilon hat itself doesn't arise there. So therefore there is no question of having an R in such a
So whole assumption
situation.
is not
Yeah.
suitable.
Exactly, right. So there and again, in a sense it becomes simpler because you have only one kind of small parameter to deal with. So you really don't need to bother there. In terms of beam or a plate, you only have the geometric small parameters. But just that the strain, pretty much you have to take all the terms into account because of that fact, and then that brings in additional complications. So the theory based on this range is for the rest of the beams other than class R, namely class S and class T, but except for the situation where the class S is not axially loaded, which was already considered in the previous case. So primarily for class T beams, and then for a large category of class S beams, because many situations class S beams, for example helicopter rotor blades, etc., they are axially loaded. The centrifugal forces are pretty large. In fact, that's one of the larger loads which cause the dominant stresses apart from others. So that in such situations you cannot consider small local rotation. You have to deal with moderate local rotation, which in turn means that the analysis, the cross-section analysis, is no longer going to be linear. It's going to be non-linear. We'll see which are the terms which are important there. Now, at least one component of the local rotation turns out to be larger in magnitude than the maximum strain. So that's basically what happens in such a situation, because you see that R is less than 1 basically means that your phi is going to become bigger than epsilon hat, okay, because of the fact that epsilon hat is less than 1. So this is quite clear, and of course phi is the maximum value of any of the three components, so it doesn't mean that all three components of the local rotation will become large. Even if one of those three becomes larger than the strain, then this is the category in which it falls. So this case yields the rotation. Once again, we go back to the general derivations that we had, and we are just specializing it to this case where R is between half and 1. And in such a situation, we see that phi tilde is approximately equal to chi tilde, and the strain, you might have to consider additional terms like this, which involve the local rotation in addition to E. So there is a term which is purely involving the local rotation. So apart from contributing to chi tilde, the local rotation will now also contribute directly to gamma. So that is what you are observing in this kind of a situation. Again, this division between what it contributes to and what it doesn't is all mathematical, because we have introduced these additional variables and we are basically speculating based on that. But they do have certain physical relevance because each of them has a certain meaning, and that helps us to interpret what happens in the various classes. So once again, you have the further higher order terms as well, and usually we just take these two results. In the previous case, we just took phi tilde or rather phi tilde to be 0, that is there is no local rotation. In other words, it's a higher order term, approximately 0, and we took gamma to be just E. In this case, we have to take your phi tilde to be chi tilde, which is the antisymmetric part of the deformation gradient matrix, and then you have to consider these 3 additional terms along with E when you're getting the deformation gradient tensor. But as I said, in this case where you have to do a nonlinear cross-sectional analysis, instead of going through this roundabout manner of introducing this Bjermann-Cauchy strain tensor and doing speculation over this, etc., it is not even necessary to do that. You can directly take, for example, the Green-Lagrange strain definition that we had, which is nothing but chi transpose times chi minus delta by 2. Of course, in the previous class we looked at an equivalent tensorial definition in terms of the dyadic, strain dyadic. Here we are looking at it in the form of just in the form of a matrix equation. So your gamma is equal to chi transpose times chi minus delta by 2. If you take that as it is, then that alone would be sufficient, and all the results that would follow from this would be, at the end of the day, it would be the same as what would follow if you were just taking these terms here, because all that we are interested in is the first order nonlinear terms, because that pretty much gives results which are acceptable for most engineering purposes. So in that sense, it might sometimes be convenient just to start with this and use the exact relationship as it is without having to bother about dropping off these higher order terms, etc. So both these starting points, whether you talk about Green-Lagrange strain as the starting point or the Bjermann-Cauchy with the moderate local rotation approximation as in this particular equation is concerned, whichever is the starting point, they, as I said, in both cases produce the same nonlinear cross-sectional analysis, by which we mean the results are the cross-sectional stiffness matrix, which relates the axial force and the bend and the transverse shear forces, the torque and the bending moments to the corresponding 1D strains, which are the extensional strain of the reference curve, the transverse shear strains, and the curvatures, which involve the twisting curvature twist per unit length as well as the bending curvatures. The other result, of course, in the cross-section analysis would be the recovery relations, and they would again be identical irrespective of whether you consider the Bjermann-Cauchy strain tensor with the moderate local rotation approximation or the exact Green-Lagrange strain itself. So next we will look at a procedure to formulate the expressions for each of the components or measure numbers of the Green-Lagrange, rather the Bjermann-Cauchy strain and the local rotation components. Remember, these phi I are the ones which populate your phi tilde antisymmetric matrix. There are just 3 components to the local rotation vector, phi 1, phi 2, phi 3, and we want to look at a procedure to formulate that. And once we have that procedure in place, we will apply it to a simple example. So now we saw that we saw 2 cases. The first case was the so-called small local rotation theory, which is valid for class R beams, in which case we don't even need to bother about local rotation, just take it as 0. Again, we're talking about only the 0th order approximation, which is a leading approximation for which this is valid. And then you take the gamma as just the symmetric part of the deformation gradient matrix without the identity matrix. Then we have the second category, which is the moderate local rotation theory, which is valid for class T and predominantly for most problems of class S beams. Then in such a situation, local rotation is no longer 0, it becomes equal to the antisymmetric part of the deformation gradient matrix, and we have additional terms contributed from the local rotation even for the Bjermann-Cauchy strain. Now this E and chi tilde are therefore needed in order to obtain all the expressions for eventually the strain energy. So because E is required because it appears over here, and chi tilde, which is equal to phi tilde, is also required because phi tilde appears over here. Or in other words, here phi tilde can be replaced as chi tilde, and therefore you can see that two quantities are therefore needed. One is basically E, which comes from the symmetric part, and the other is the chi tilde, which comes from the antisymmetric part, both from the deformation gradient tensor, of course, or the matrix rather. So chi, which if we need these two, that is the symmetric and the antisymmetric part, obviously we need the deformation gradient tensor, which in turn means that, and of course E is related to chi, and chi tilde is related to chi in this way. This is what are the definitions we already introduced earlier in today's class. So if chi is needed, obviously you need the covariant basis vectors and the contravariant basis vectors of the deformed configuration and the undeformed configuration respectively. So let's recapitulate that. The deformation gradient tensor chi is given as the juxtaposition of the covariant basis vectors in the deformed configuration and the contravariant basis vectors in the undeformed configuration, and basically your chi is given in terms of this because we expanded in a mixed formulation. The reason why we are bringing this back into picture is that when we introduced it, we were only talking about dyadics and tensors. Now everything we have reduced it to a matrix notation, so we would like to reduce that into a matrix notation as well, so that we know how to determine these chi ij. So that's basically the reason why we are bringing this back, because we need a procedure to get expressions for the strains and the local rotations. So now the measured numbers of the deformation gradient tensor, just like any other dyadic, if you have and you want to expand it in a set of two bases, all that you have to do is to take the dot product on the either side with respect to those bases. Okay. So an equivalent form of stating this is to state that your chi ij is given by chi dotted with the big B's on this side and the small b's on the right hand side, and we bring in the expression for the chi itself from here and we put it over here, and instead of putting the brackets around this, we take it out and put the brackets around this, so that we can evaluate this dot product of two vectors as a scalar measure number, and again the dot product of this as a scalar measure number, and then we have to just multiply those two scalar quantities to get the scalar quantity, which is a particular measure number of the deformation gradient matrix. So this is how the actual evaluation is supposed to take place. Now your chi ij is very easily obtained, because if you see in the first bracket, what you have is both uppercase quantities, or in other words quantities associated with the deformed configuration, and in this other bracket what you have is both lowercase quantities, small g and small b, which means they are associated with the undeformed configuration. And we already know that the small g's, it's very easy to derive in terms of the small b's, and the big g's are easy to derive in terms of the big b's. So they are already there. All that we have to do is to take the dot product as it is without having to rotate it or transform it to another set of coordinates and then multiply those. So it's convenient to resolve the base vectors of the undeformed state along small bj, that is to get the measure numbers of these along this, and of the deformed state along bi. So it's easy to get these in terms of the big bi's. And the brackets in kappa ij, the way we have placed the brackets over here, which implies that in order to find all the quantities of interest for us hereafter, which is basically the deformation gradient matrix, the local rotation vector expressed as a column matrix, and the Bjoerman-Boyakoshi strain expressed as again as a 3x3 matrix. Now for all of these, since we have already got everything into matrix notation, even though here there is a tensor notation, once we have put the brackets in this way, instead of putting it around this, we have got rid of the tensorial notation, the juxtaposition and things like that, and we are only talking about scalar quantities and matrices which have their elements as scalar quantities. So no tensor analysis is required beyond this particular point. So next what we will do is to look at an example which illustrates this procedure. This is the general procedure. So now we have to see a special case where we can actually evaluate analytically these dot products and then multiply them to get the expressions for chi ij, and in turn, once that is there, once chi ij is there, we can get its symmetric and antisymmetric parts. Then we can get the local rotation, substitute that here, and this is the symmetric part of chi, of course, and then we'll be able to get an expression for the Jaume-Cauchy strain matrix. So this is the preliminary example that we will take up. It is to formulate the strain and the local rotation measure numbers in initially curved and twisted beams. So as far as the initial geometry complications are concerned, we are not doing away with that. We are allowing for initial curvature and twist even in this simple example. But the red quantities that you see in both places are the things that we are simplifying purely for pedagogical purposes. Not that this is not useful, just that it is for a very restricted class of problems. So what is that major restriction that we are bringing in to keep things simple or tractable for a classroom kind of an explanation? We will say that there is no cross-section in plane warping. In other words, when I extend this, for example, there is a Poisson-like effect. Those kinds of things are ignored here. Only the out-of-plane warping is taken into account. And this you are very familiar with in one of the theories in aerospace structures, basically, or for that matter, any thin-wall structures, basically is the St. Bernard warping solution that you have. In such a situation, you do allow for, whenever the cross-section is non-circular, you allow for out-of-plane warping, but you do not allow for in-plane warping. So it's a similar kind of a situation that we are going to deal with here. So now we'll take up an example illustrating this procedure. Already you are familiar with this picture. Now we are just bothered about, let's say, the undeformed state. Some general cross section we have over here, and we introduce the unit vectors b1, b2, b3. The way we introduce b1 is quite clear for all of you. It's just the tangent to the undeformed reference curve, and how we choose the undeformed reference curve again is according to convenience. It could be the loci of the centroids, it could be the loci of let's say the shear centers, loci of some corner of a rectangular cross section, whatever. In the case of a wing, it could be the loci of the mean aerodynamic centers. But once you have chosen it, you have a particular curve which demonstrates the one-dimensional aspect of this beam, and then you take the tangent unit vector to it along the entire length of that curve, and that's basically what you represent as b1. So that's quite clear, that is your tangent b1. Now suppose this particular curve, the reference curve, takes on a shape something like this. For example, you could have a helical spring, and you could consider the helical spring as a one-dimensional structure. Even a helical spring, in other words, can be analyzed using the so-called beam theory that we are developing here, using a one-dimensional model for that. So in such a situation, it need not be a helix with a constant radius or whatever, but some shapes similar to a helical spring, for example, or for that matter, any general shape where you have initial twists and curvatures such that the entire reference curve is not planar. It is different from a planar curve. Okay, so in such a situation, which is the most complex situation that you can think of, you can have a special way of introducing the other two unit vectors. We already talked about b1. Now the question is, how do you introduce b2 and b3? Again, you have the freedom how you want to introduce it. One way, of course, in the case of a rectangular cross section, for example, is to introduce x2 and therefore b2 along the width, and x3 and b3 along the thickness. So that is definitely possible. But there, in some cases, it becomes easier if you do it along a special mathematical way of defining b2 and therefore b3. Because once b2 is defined, b3 gets automatically defined because this is an orthonormal system. So b3 is a unit vector, its magnitude is fixed, and it has to be perpendicular to both b1 and b2. So if you have fixed b1 and b2, it just becomes b1 cross b2. So you don't have much play over b3 once you have fixed b2. It's the same way, if you fix b3, then you don't have any freedom in how you decide b2 will be. So let's say b2 is defined as what is very familiar in the geometry of curves, using a vectorial analysis for that. In such situations, it's common to define a normal such that it is defined in terms of the tangent. The tangent is already determined. B1 of course is determined as the derivative of the position vector to this reference curve. So that is quite straightforward. You know how that is defined. Now we can, for example, define the B2 as the normal such that it is B1 prime gives the direction of it, and because it's a unit vector, it has to be divided by the magnitude of B1 prime. So it is B1 prime divided by B1 prime magnitude, and then you have the so-called binormal, which is the B3, which is nothing but the cross product of these two. So that's why you see that it is B1 cross B1 prime divided by the magnitude of B1 prime. So this is called as the binormal. So this is one way in which you could introduce these quantities, but not necessary. This is just to give an example of the different ways in which you could introduce these quantities. So now let's talk about an initially twisted and curved beam. And in such a situation, we'll introduce the small case to represent the initial twist and the initial curvatures as K1 and K2 and K3 respectively. So Ki Bi, where there is an implied summation over I, is giving you the vector K. So this is not a column matrix representation of the vector, it's a general vector that we're talking about because Bi is a vector. So in other words, when you write, you will have an underline over here and an underline over this as well. So the curvature vector of the undeformed beam, and this kind of notation for the curvature was initially introduced in Love's textbook in 1944. So now the K1, as I said, is the pre-twist of the beam in general, but when you have a complex situation like this where the entire reference curve does not lie on a single plane, it goes outside a plane. In such a situation, when you have that, then K1 not only includes the so-called pre-twist, which is defined as how one cross-section is at a different angle with respect to another, divided by the length. So that is basically what you're looking at. And of course, it's a function of x1. It can change along the length. Some parts of it could be untwisted, or in other words, no pre-twist, and there could be some parts where there is twist, and the twist can vary as some function along the length as well. So in all such situations, you would have just the pre-twist of the beam if the entire reference curve was on a plane. Now if it is not on a plane, that K1 not only includes that I just talked about, the angle between two cross sections divided by the length or distance between them, but in addition there is something which is associated with the geometry of the curves, which is called as the line torsion, so the curve's torsion. So the undeformed reference line's torsion, and that in turn is defined in terms of these. So that's the reason why I introduced this. Though it is for most structures problem not necessary to bring in these concepts in order to introduce B2 and B3, it might be necessary in some beam problems where the entire reference curve doesn't lie in a plane, that when you talk about K1, you recognize that not only does it include the change in angle between cross sections, but for example, in a situation where there is no change in angle between cross sections, you might still have non-zero K1. That's what I'm trying to say. Okay, so and when you have a situation where there is a change in angle between various cross sections without load, even in such a situation, if the reference curve is not in a plane, you still have to add this particular term, which is defined entirely in terms of B1, the tangent, which already you know how to determine. So it's only in situations where this quantity is non-zero, of course, you need to be worried about this, and that is the situation, as I said, when the curve is non-planar. Next, of course, the other two are fairly straightforward. K alpha, nothing but the components of the, or measure numbers rather, to be more specific, of the curvature of the undeformed reference line. The reason why I'm distinguishing between components and measure numbers are for most of the parts, though I made a mistake over here. When I say measure number, I mean a scalar quantity, whereas when I say component, I should strictly speaking refer to a vector, because if it's a component of another vector, it has to be a vector as well. So the right way to say this is K alpha is the measure numbers of the curvature of the undeformed reference line due to the curvature of the reference curve itself. So then we have a recap here. The fundamental kinematical analogies. Remember, we introduced derivatives with respect to time and variations. So, and also the in that situation we introduced a third level where we talked about derivatives with respect to the spatial coordinate, which was x1 in the case of a curve, and we bring back that into picture here. The fundamental kinematic analogy for involving this initial curvature vector that we have introduced here is something which is associated with the spatial variation, just like the angular velocity was associated with the time. So remember that if you have an angular velocity of this frame B, so remember right now we are only talking about initial twist and curvature, so we are only talking about initial angular velocities here. It is the angular velocity of the small b with respect to the A frame. So the A could be the aircraft fixed frame and B could be the body fixed frame. So there could be an angular velocity. A very typical example can somebody give for the omega BA not being 0? A typical aerospace example?
Flapping wing.
Flapping wing, sure. Another situation? Be an aircraft engine blade or a helicopter blade, for example, right? So in all such situations, the beam as a whole, even before it deforms, it can have an angular velocity. In other words, the undeformed configuration can have an angular velocity with respect to the aircraft. And in addition, because of the deformation, there could be other angular velocities which are creeping up, which would be much smaller in magnitude. Now, there we would say that, of course, these are derivatives of unit vectors. When we take, remember that we should mention the frame in which we are taking the derivative, because all derivatives are with respect to A. We are not specifically mentioning that, but strictly speaking, that has to be mentioned as well. So when I say Bi prime, I refer to the derivative of Bi with respect to x1 in the frame A, and similarly here it is the derivative with respect to time in the frame A. So Bi dot is going to be given by omega cross Bi. So that is something we already discussed in one of the earlier classes. Now you look at the beautiful analogy between this and this. All that I'm changing is the dot to the prime and the omega changes to k. So the same role which is played in a temporal sense by the angular velocity is played in the spatial sense by the initial curvature vector. So that's the significance of that, and that analogy can be taken further to get expressions for a lot of quantities without having to rederive the whole thing, because we have looked at this in a much greater detail. We'll take advantage of that in deriving certain things related to spatial derivatives and curvatures as well. So now let's look at how we derive for this example case the covariant basis vector for the undeformed beam. So remember that this undeformed beam is quite complex because we are allowing for initial twist and curvature. So it's a very general example as far as the undeformed configuration is concerned. So now we talk about this reference curve or reference line that we have over here, and that is identified by setting x2 and x3 equal to 0 in the general position vector. So from some frame A, which is, let's say, aircraft fixed or vehicle fixed, we are basically drawing these position vectors, one to the reference curve and the other to any point on the reference cross section at the same point at which R is defined. So for the same cross section on which that particular R refers to as well. So that is basically your R hat, not necessarily at the periphery but anywhere within the domain of this undeformed configuration. But you can get R as a special case of R hat by just setting x2 and x3 equal to 0. So the position vector to any material point R hat can be obtained as R, which is a function only of x1, plus x2 along b2 and x3 along b3, which is basically the unit vectors that you have introduced here, and not necessarily the normal and binormal that I talked about in the previous slide. That was just to illustrate what is the significance of K1, that it can contain not only rotations of cross section but also the torsion of the curve. It's purely for that purpose that I introduced that notation. It is not necessary that B2 and B3 are those. Okay, B2 and B3 can be chosen according to your convenience, and X2 and X3 are along those. So you have X alpha, B alpha with an implied summation over alpha, and because it is an initially curved and twisted beam, not only is R a function of x1, but more importantly, B alpha is a function of x1. For example, if it is initially twisted and I take the B2 and B3 such that for a rectangular cross section B2 is along the width and B3 is along the thickness, if it were twisted, then a cross section here and here would be something like this, and you see that B2 is along this direction, B2 is along this direction, and in other, with respect to frame A, these two are different vectors, and that is what is mentioned by the fact that at different values of x1 you can have B alpha as function of x1. Of course, B1 is also a function of x1 because of the initial curvature that you are having. For a straight prismatic beam, your B1 would be constant throughout. So once again, let's bring back the definition that we gave for the covariant basis vectors. They are nothing but tangents to the coordinate curves. So your G subscript I, again small g referring to the undeformed configuration, and small g subscript I is the partial derivative of r hat with respect to xi, because we are looking at gi, and this derivative has to be taken with respect to the frame A from which we are considering these position vectors here. So now we can actually evaluate this, because we can substitute for r hat as r plus x alpha b alpha over here, and while we take those derivatives, we have derivatives with respect to x1 as well, and to actually bring in the concept of the initial twist and curvature, which are part of the curvature vector, we will utilize what we looked at in the previous slide, namely bi prime is equal to k cross bi. So that will be utilized in order to take some of these derivatives. For example, here you would have in g subscript 1, you would have dou r hat divided by dou x1, and you would have, let's say, B2 component coming here. So how do you get B2 prime? So then you would take advantage of this and take it as just k cross B2. So that's basically the reason why you need this. And of course, you will have R also coming into picture here, and when you determine G1, you need an R prime, and there we will take advantage of this equation as well, that R prime is equal to B1, so that we can express everything in terms of B1, B2, B3 and K1, K2, K3. So that is the intent. So the covariant vectors for in this particular case turns out to be G1 is equal to, it's quite easy to do that. You would see, of course, derivatives of x2 and any of the x's with respect to the other x's are 0, because they are independent coordinate measures. So the only derivative in this particular case would be with respect to b alpha, unless the derivative is with respect to one of the x alphas itself, in which case it would have a contribution as well. So G1, for example, has a B1 component, a B2 component and a B3 component, whereas your G2 and G3 have only B2 and B3 components. That is quite easy to see, because you have to take the derivative of r hat with respect to x2 in order to get G2. If you want to take the derivative with respect to x2, you see this is not a function of x2, and here b alpha is also not a function of x2. The only place x2 comes is in the term x2 b2, and therefore that would just become b2. Similarly, your G3 would also be equal to b3, and this is, remember, is the most general case. We are allowing for any initial twist and curvature to be present simultaneously, and also to change if it wants along the entire length. So even for the most general case, you see that G2 and G3 are B2 and B3, and this is not surprising, because the covariant basis vectors are nothing but tangents to the coordinate curves, and the coordinate curves we have introduced are x2 along B2 and x3 along B3, or in other words, we have said that those coordinate curves are straight lines, and we are just introducing B2 and B3 parallel to them. So it's quite obvious that G2 and G3 small G2 and G3 subscripts should turn out to be B2 and B3. On the other hand, the entire complication due to the initial twists and curvatures are appearing in the covariant basis vector G1, where you have the contribution of K2 and K3 to the B1 component, and you have the contribution of the initial twist and of course the torsion of the curve itself, if it were present, to the B2 and B3 components of G1. Next we get the contravariant basis vector, which is nothing but the perpendicular to the surface formed by pairs of the covariant basis vectors. So just a cross product of those covariant basis vectors that we already derived would be sufficient to get the contravariant basis here. So just repeating what we had on the previous slide, G1, G2, G3 have in general B1, B2 and B3 components, but you see that G2 and G3 are much simpler, and this is the general expression for G1. So now we go back, we defined a particular quantity which is the metric tensor. Now we are talking about everything in a matrix form, so we will need the determinant of that matrix over here. So that determinant would be obtained by taking the dot products of the covariant basis vectors in pairs, including with themselves, and populating a matrix M and N varying between 1 to 3, and then you take the determinant of that matrix, and we will call that particular quantity as G. And then if that quantity were G, it's quite obvious to see that the square root of G would be nothing but this particular thing. Because of the fact that G2 is only B2 and G3 is equal to B3, it becomes very simple, and it's only this particular term which contributes to the determinant, and that turns out to be this particular expression. And we will denote that quantity as by a notation root G. Now we just recap that to determine the contravariant basis vectors, we know that they are perpendicular to the surface formed by the covariant basis vectors. So in general they are defined in terms of this, the cross product Gj cross Gk summed over J and K along with the permutation symbol over here, and divided by 2 root G. The factor 2 is because Gj cross, so let's say G2 cross G3 to determine a G1 would also have a G3 cross G2, and that would be negative, so there will be 2 contributions, and then you will have to divide by 2 to do that. So in this simple case, you can just write that, for example, G1 would be just G2 cross G3, that will give you something which is perpendicular to that surface, but also to take care of the fact that the covariant basis vectors and the contravariant basis vectors, when taken as a pair, should basically lead to the Kronecker delta, for example, when you have a dot product, so that as a combination they work with similar properties to orthonormal basis vectors, though the covariant basis vectors themselves are not orthonormal. That's something which is easy to verify in this case also. You see that G2 and G3 are perpendicular to each other, but not necessarily to G1. Again, G2 and G3 have a magnitude equal to unity, so they are unit vectors, but G1 in general is not a unit vector. So this particular set is not in general an orthonormal set of basis vectors. If you take the special case where all the initial twists and curvatures vanish, these two terms will go, and therefore G1 would also just become B1, and just like the small b basis, your small g basis subscript with subscripts would also be an orthonormal basis, and that's again something quite intuitive. So coming back, your G1, so that is the reason, because you want the pair of the covariant with the contravariant to function with properties similar to the orthonormal basis, that not only you have to get the cross product to get us a vector which is perpendicular to both or to the surface formed by both, but you also have to divide by root G, so that for example when you have G1.G1 or G2.G2 and G3.G3, they all give value of unity. So that's why this particular thing comes, and that of course gels well with the general definition here as well. So now you can easily do that. G2 cross G3 would just be B2 cross B3, which would be B1 divided by root G, which in turn is dictated only in terms of the initial curvatures, but not in terms of the initial twist. Then similarly you can get the expression for the second contravariant basis vector. So now that has
by 2.
No, let's see, that is, you will have a G2 cross G3 plus a G3 cross minus a G3 cross G2 divided by 2 root G. Minus G3 cross G2 is equal to plus G2 cross G3. So you'll have 2 G2 cross G3, and that 2 will cancel with this 2, and therefore you'll have only G2 cross G3 divided by root G. Okay. And now we come to the second contravariant basis vector, which is defined similarly by changing these superscripts and subscripts in a cyclic manner. When you do that, it is G3 cross G1 divided by root G, and there you see that apart from here, you see that G1 is parallel to B1, though it's not a unit vector, but G2 is no longer parallel to B2. Unlike this G2 in the covariant system, it was B2, it was parallel to B2 and equal to a unit vector. Here it's no longer a unit vector, and it is also having a component which is parallel to B1 as well. So because of the initial twist. So once again, it goes with the fact that I was already talking about. So that basically brings in the effect of K1 onto the contravariant basis vectors here. And G3 is very similar to G2. Instead of B2 you have B3, and instead of X3 you have X2, and instead of course you have a minus sign because of the way the thing is structured. Okay, so that is basically the contravariant basis vectors as far as the undeformed beam is concerned. Now we introduce the ad hoc assumptions. So far whatever is done is general. There is nothing that we have simplified. It is for a very generic problem. The most complex beam problem that you can think of, all the results that we had in the previous slide are valid. Now just for pedagogical purposes, we will assume that the reference cross section does not distort in plane, or in other words, the three-dimensional warping field which exists in general, we will say only W1 is non-zero. W2 and W3, represented by W alpha here, are both equal to 0. Then the out-of-plane warping we will assume is like a Saint-Venant field. Again, this is an assumption because at different cross sections you could in general have different Saint-Venant warping function, but that is not taken into account. A single Saint-Venant warping function is chosen in terms of how it is a function of x2 and x3, but its amplitude is a function of x1. At different locations along the length of the beam, the magnitude can change, but the overall shape in terms of how it comes out of the plane or goes into the plane at different locations in the cross section is one and the same. So this is an assumption that we make over here, which we will relax when we go to the more general example in tomorrow's. Actually, in Monday's class, I would like to have a special class on Monday if that is convenient to all of you. So in Monday's class, we'll look at a general example of that. Now these ad hoc assumptions that we are going to use for this example, which probably will continue in the next class, first half of the next class. So these ad hoc assumptions are merely, as I said, for illustration, only for today's class and the first half of next class. The general theory does not require such assumptions, which is what we will do at the latter part of next class. And the full 3D strain field is treated by a general displacement field, where we will allow for W2 and W3 not being 0, and also the fact that we will not make any specific assumption about how the out-of-plane warping behaves. It could be a much more general function of x1, x2 and x3 than the kind of a separation of variables kind of a form that it has over here. So I think with this I will stop. In the next class we'll get into the deformed beam geometry for this special example.